thanks all for joining us for today's presentation. What we're doing today is part one of our ongoing Night School series. Night Schools is something we do for our customers about once a quarter, about 4 times a year, and they're a presentation around a certain area of SOLIDWORks. And for this particular run through, we've selected stress and a little bit of flow analysis in SOLIDWORks, talk about how they work. And we ran this through 6 cities up and down the West Coast a couple of weeks ago, and this online version is for everyone else who wasn't able to make those sessions. So the title of the Simulation Night School is Stress and Flow Analysis in SOLIDWORks. And to start with today, we're going to talk about the basics of stress analysis primarily. And we're going to look at, some of the underlying tactics or underlying assumptions that are part of stress analysis in SOLIDWORks, with a focus particularly on the static stress analysis type that is part of SOLIDWORks Premium. It's by far our most common, most widely used stress analysis module, so we'll focus on that today. We're going to walk you through the analysis process from start to finish. We'll talk about some of the tactics and techniques you use to get through an analysis setup, and we'll talk briefly about results and interpreting those results. So that's part one. That's going to run roughly an hour today. Part two, we're running on Thursday, same time, same place, and where Damon will take you through some common problems and troubleshooting issues that we see people have, results not matching expectation, analysis not running because of different conditions, meshing issues, those sort of things. And we'll also introduce the SOLIDWORks flow simulation analysis process on that. So tune in on Thursday for those last 2 things. But to start off today, one of the things that, I'm going to be presenting some different times and some different statistics as we go through. One of the questions we always get is, what sort of computer do you have? If you're getting these great analysis times with a supercomputer, that doesn't make any sense to me with kind of a computer I bought from Best Buy. So, to let you know what I'm using. What I'm using as I put together this presentation, it's an HP laptop running an Intel i7 chip at 2.6 gigahertz. It's a 4-core chip, and I only have 8 gigabytes of RAM. It's a good, solid engineering workstation. I run everything that our customers send to us on this workstation, but it's getting a little old. It's probably a little underpowered, particularly in the RAM sense. One of the nice upgrades I just made recently is an SSD hard drive that's kind of changed everything in terms of the speed that I can do computing, launching, booting, those sort of things. So let's talk about the concept of stress analysis. And we're going to focus to start with on this thing called linear static stress analysis, which is probably about 80% of the stress analysis performed today. But what's important to realize is that linear static stress analysis comes built in with a couple of assumptions that are always being made. First one is that we assume that any loads that are being applied gradually or slowly. If I'm applying a load to the table that's in front of me right now that you can't see, I'm pushing gently on that table until the full load is applied rather than striking it with my hand or something like that. So we assume that loading is static, basically. And if that assumption is no good to us, we need to move on to a dynamic analysis type instead if we want to analyze a shock or an impact or a vibration or anything like that. The other assumption we make is that there is linear material behavior. So we assume we model the stiffness of whatever materials we're working with as a straight line stress strain curve with a given slope. What that means is if we apply 1 pound of load and it moves 1 millimeter, if we apply 2 pounds of load, it will move 2 millimeters. We don't need to run that second study. The model will respond linearly to changes in loading. And so another part of that is we assume small deformations. We assume that as the model is loaded, its shape does not significantly change, and the stiffness of its shape doesn't change. So if I'm analyzing, the load, if I drive a truck onto a bridge, I expect that when that truck goes onto the bridge doesn't change shape drastically. If I'm looking at it from afar, I shouldn't see the shape of the bridge change. But if I'm to push on a rubber seal or something, I will see a visible shape change as I apply that force. And so only no visible shape change or minimal shape change is appropriate for linear analysis. And if we want to overcome either of those assumptions, we're moving to a nonlinear situation. So there's a couple of assumptions, but the great news is for the vast majority of engineering analysis that is done today, operating under a linear static set of assumptions is a pretty good approximation for the vast majority of things. The one thing that we also, well, first of all, here's just a kind of visual illustration of what we just talked about. All right. For this case, where the beam loaded by some sort of weight, right? Our linear case is where the weight is just sitting there and it's small enough that it doesn't cause a drastic deformation of the beam. The situation where we would drop the weight, that would become dynamic. Situation where we have a very large weight that causes an extreme deformation, that's going to become nonlinear. And if we have a situation where we're dropping the weight and it's causing a large deformation, that's going to be nonlinear and dynamic at the same time. And we can handle all of those in SOLIDWORKS. They're just different modules. The other thing that's worth considering when we look at linear static stress analysis, if you start off by looking at sort of an experimental stress strain curve for something like steel or aluminum, right? It's going to have something like roughly this shape. The straight line portion below the yield strength, and then some sort of non-linear behavior afterwards. Linear static stress analysis makes this assumption. It assumes that the slope of the stress strain curve matches the linear portion, but it goes from 0 to infinity. And what that means for us is if we do happen to load the object beyond its yield strength, the software will happily report a stress level well in excess of that yield strength, which is not realistic. Okay, so if you've got a situation where a model is being loaded and it's reporting stresses above the yield strength, all you can really take away from that analysis is the knowledge that the material has yielded. And from a design perspective, that's often that's all we need, right? In many design cases, yielding equals failure. So if we see material yield, we need to redesign the part. As we get into nonlinear analysis, we can make different approximations of post-yield behavior, either a simple, what we call bilinear model, or we can get into actually modeling the complete true stress strain curve. Engineering stress strain curve, to use the exact right term. So it's very important to understand those assumptions up front before you jump into an analysis. If you have a situation that deviates, that breaks those assumptions, you need to be considering that as you go into the analysis process and using the right tool for the job. Every single license of SOLIDWORKS has a limited stress analysis tool. It's called SOLIDWORKS SimulationXpress. It uses the complete analysis engine that we're going to talk about today, but it has some limitations. Okay. has exactly a very similar interface to the complete analysis tool. So you do things pretty much the same way. But these limitations are that it can only run stress analysis on single parts. It can only do force or pressure loading, no torque, no remote mass, no distributed mass, anything like that. It can only fix restraints. You only have global control of mesh density, and you just see 3 result plots with minimal post-processing capabilities. But it does offer a single factor optimization tool. You can tell the software something like adjust the thickness of this plate until it doesn't yield anymore, or adjust the thickness of this plate until the factor of safety is greater than 2. Okay, so that is available. Realistically, this is a good tool. It uses the same engine as the full tool, but some of these limitations can mean for anything other than a first pass analysis, it's not complete enough for our needs. But what we're going to focus today's presentation on is the simulation static analysis type that's part of the SOLIDWORKS Premium analysis, SOLIDWORKS Premium CAD bundle. It's the blue bubble over here called static analysis. It's 80% of the stress analysis that's done today is done right in that module. We do offer other analysis capabilities. Our Simulation Professional package introduces frequency and buckling, some thermal and optimization routine. A Simulation Premium package offers nonlinear and dynamic analysis. The good thing about the SOLIDWORKS analysis interface is that the processes and the techniques are identical, well, very similar, regardless of what analysis type you're doing. So if we learn good practices here in doing static stress analysis, they're going to be equally applicable for any other analysis type on the screen. That's why we're focusing on that one. It's definitely the most common. It's the one most people have. But you can apply the practices we'll talk about for meshing or troubleshooting or whatever to everything else in this screen here. And later on, we'll talk about flow simulation as part of part 2. So when you're looking at the analysis process from start to finish, it often involves a little more than what we talk about within the simulation tool. And generally, we start every analysis process with some sort of geometry. Right? It might be a production model that's being developed to develop the manufacturing drawings. It may be some dummy geometry that's been developed only for FEA. But an important first step is to consider a simplification step. Basically, anything that is represented in the model that doesn't affect the strength or the performance of the object is extra information that's going to take you longer to get your answer. And so often it's good practice and a wise use of your time to spend 20 minutes eliminating detail, like the name of your company stamped on the faceplate of the object, or nuts, bolts, and screws that we might choose to represent differently. Spending 20 minutes simplifying a model there can pay off in spades later in the process when you might save 5 minutes per analysis run, but you typically have to run an analysis 5, 6, 7, 8 times as part of your analysis process. The next phase, once you get a simplified geometry, you can use the production geometry if you wish, there's nothing stopping you, is to apply the mathematical model, to apply the conditions, and that's where we're going to focus today. Next phase after that, is to mesh the model. Talk about that a little bit, and we'll talk about a lot more in the troubleshooting type section, and then get our results and make an assessment from them. I meant to say this up front, but I don't think I did. This presentation is being recorded and will be posted on our website. Find it under the Events Recorded Webinar section of our website. The slides will also be made available to you, and a link to those will be distributed after the session. Okay, so now let's work through this analysis process that we talk about. This is really what we do inside the software as we're developing an analysis model. And the good thing about it is that the process you need to take fairly closely mirrors the tree that is structured in the analysis environment. So you pretty much start at the top and work your way to the bottom. So we're going to look at materials and model definitions. We're going to look at contact, connectors, fixtures, loads. We're going to mesh, solve it, and look at the results. The general process. So let's start off and talk about the materials. SOLIDWORKS ships with a number of material, and you should always check that your materials, the specific ones you're using, match those parameters. So a couple of things to point out before we get started. This is a model we're going to be working on throughout today. It's basically a tank, right, filled with liquid and mounted on a weldment frame. Okay. So first things first, to access the full simulation tool, if you have SOLIDWORKS Premium or above, you want to go to Tools, Add-ins, and turn on the Simulation option. That's going to give you access to your simulation menu and your simulation tree if you've got any studies created. If we create a new study from scratch, one of the first things you'll notice, if you expand the parts folder, any object that had a material defined in SOLIDWORKS is automatically populated here. And the SW designation tells you that that material definition came from SOLIDWORKS. If you want to modify that, you certainly are able to. And the best way to do that is just to right-click and go Apply Edit Material. One thing you'll notice is if you look in the SOLIDWORKS Materials library, nothing in here is editable. Right? I can't click and I can't modify, and that is by design. It means that if you go into that library, you know that one of your colleagues or an intern or someone like that hasn't modified it. But if you do want to modify one of the existing SOLIDWORKS materials, the best thing to do is to right-click and copy. To come into a custom material database, you'll see a blank database at the bottom, and paste, and then that material becomes fully editable. Right. You can create your own materials, and we certainly recommend you doing so. You can even put a custom library on a network drive or something like that and have everyone refer to it. The location is just defined under Tools, Options, File Locations. So you can all share and populate a common material library. But there's two pieces to this parts folder. One of them is the material definitions. The other is something a little more involved. It's the representation of how the object is going to be modeled. And we have three representations we can utilize in SOLIDWORKS. Objects can either be represented as what we call shell, beam, or solid mesh. Shell mesh is applicable for thin objects with a constant thickness. Beam mesh, so a typical best case there is sheet metal is a good example of something that's applicable for shell mesh. Anything that's long and slender, has a constant cross-section, can be treated as a beam mesh. Weldment frames are automatically treated as beam mesh. And everything else is treated as solid mesh, so it meshes through the thickness of the part. Just to talk about those three mesh types, solid mesh is a tetrahedral mesh element. The default element has 10 nodes and curved sides. It's a parabolic second-order element. And one of the things that we look at to kind of estimate the strength or the accuracy is the number of degree of freedom available in each element. And that's really a parallel to the number of stress equations that get run for every element. So in this second order element, which is the most common usage, each element has 10 nodes, and each one of those nodes can move in 3 orthogonal translational directions, X, Y, and Z. And so we talk about this element having 30 degrees of freedom. Now there is the ability to create what we call a draft element. It's a first order element. It has straight sides, so it doesn't map to curved geometry, and only 4 nodes. And that only has 12 degrees of freedom. If we look at thin geometry, right, when we do a shell mesh, the key difference is we don't mesh through the thickness. We treat that sheet metal or plate or shell, whatever it is, as a 2D surface. And again, we have options for first and second order elements. Second order is the default. This thing now has 6 nodes. The key difference here is that shell elements have rotational degrees of freedom. So each node can move in 6 directions, 3 translational, 3 rotational, which means that each element has 36 degrees of freedom, about the same as in the ballpark of the solid element at 30. So what is draft quality for? Right, we showed you these diagrams where they have essentially half or less degrees of freedom. The good thing about a draft quality element is it takes up pretty much the same space and area as a high quality element, but it solves with a lot less equations. It solves much more quickly. So it becomes a very good troubleshooting tool. Right, it's a tool that you can use as you're developing your model, as you're testing out different phenomena. Tool that you can turn on so that you essentially make mistakes more quickly. Right? If I've got a complex model and I'm not sure if I've got all my restraints right, or I haven't applied my contact correctly, I'll turn on draft quality mesh and run it. And that way, if I have got a problem and it is going to fail, it will fail a lot more quickly. And I see a question just popped in. Do all simulation packages have high and draft quality elements available? In SOLIDWORKS, all the analysis tools do have that option. In the stress side of things, if you're talking about analysis tools in general, they may call them 4-node tetrahedrons and 10-node tetrahedrons, but they'll generally have access to first and second order elements. So, one quick question is, why do we use shell elements? Well, for something that is thin geometry, it can be really challenging to map a 3D element through the thickness, especially if that thickness dimension is significantly thinner than the span dimensions in the other aspects. And so we can end up with enormous amounts of mesh and still not accurately capture maybe the bending stress or something like that. We talk about needing 2 solid elements through every thickness of a part in order to accurately capture bending stress. And that can just be not feasible with thin components. Whereas with shell, with those rotational degrees of freedom, and the fact that it acts with a similar thickness to the real part, we can really get that done a lot more efficiently. The last type to talk about here is beam mesh. Right? That's used for slender objects with a constant cross-sectional shape. It assumes the same cross-sectional stiffness as the real 3D shape, but it's represented as a line element, a single line with a node at each end with translational and rotational degrees of freedom. So only 12 degrees of freedom. Beam mesh is a very, very efficient way of representing, complex welded frames, but we do give up a lot in terms of the fidelity of the information we get out of it. For example, with a beam mesh, we completely ignore anything that isn't the cross-sectional shape. So any sort of stiffeners or holes or anything like that, we'd need to analyze those with solid mesh in order to capture those. All it captures is the cross-sectional shape and the length, basically. So what does that mean on this model that I have here? Well, when I open this when I start a new analysis, I can interrogate the assumptions that are being made throughout the object. So first of all, the frame at the bottom here was modeled with SOLIDWORKS weldments. That was the design technique I used to create them. They are automatically mapped as beam elements, and a node is placed at each join. That's those pink dots. I don't like that choice. Right-click, treat as solid, and I will mesh and analyze the precise shape of that object. These plates underneath here, these support plates, I modeled those with sheet metal, and the software has modeled them as a shell element. That will happen for all sheet metal parts. In this case, that's not the choice I want to make. I'm actually I want to have some detailed look at this interaction between the saddle and this plate and the tank. So I'm going to pick these two and say, treat as solid, and they will now be meshed as solid geometry. The support cradle is all solids. It's a multi-body part, and that's fine. But the tank here is being meshed as a solid, despite the fact that it's very, very thin. It's going to be very, very challenging. So I'm going to choose here to treat this as a shell. I'm going to pick the three surfaces, define the thickness. I happen to know it in inches, so let's use that and map that. So whatever choice the software makes out of the box, we are not bound to it by any. We can make adjustments completely. And now if I go mesh this model, what we will see, the beam elements are shown as, you know, a cylindrical tube, but they really are a solid. It's my first attempt at meshing. The shell elements are two-dimensional, and they will show either orange or gray, depending on what side you're looking at, and then my solid elements have all been meshed here. So you can see that feedback pretty quickly on the screen. The next thing we need to go think about is how these parts interact with each other, what we call contact, and also connectors, but we'll start with contact. Contact is the relationship that two parts have to each other when they come together. We're really making one of two choices for the most part. There's a couple of special cases there, but two choices. We're either saying those two parts are bonded and fused together so that if they start together, they do not separate, they do not move relative to each other, they are basically magic glued together with an infinitely strong glue. Or we say there's a no penetration relationship. It's a sliding, where two parts are free to slide on top of each other, they're free to separate, they're free, but they can't go through each other, okay? Generally the two choices we're choosing between. We need to make an assessment of that for every single interface in the model. And even for something simple like this, that could very quickly get tedious, right? Not just the interface between the saddle and the tank, I've also got to consider the interface between all these individual parts, these multi-body parts, and how they interact. So what the software does is it uses something called contact hierarchy to make that selection easier. It's not going to make us go through and define every single one of them. We're going to use this hierarchy process to define those things. So what the software does, it makes an assumption about every face that is initially touching. Calls this the global contact. Basically say, hey, every face that's initially touching, let's assume they're all bonded. Doesn't look at mates, it doesn't look at anything else, just looks at whether those faces are touching at the start of the analysis. We can set it to allow penetration, which is basically turning off all contact, saying make no assumption, I want to do everything manually. Or we can set it to no penetration. A little warning here, if you use global no penetration, it'll actually scan the model and monitor for faces that come together during the analysis, and it can be significantly slower than defining those no penetration contacts manually. Just keep an eye out for that. However, the global contact assumption doesn't apply everywhere. It first of all doesn't apply to faces that are not initially touching. We're going to have to manually address interactions between any parts that are not initially touching. Now, I should point out in SOLIDWORKS 2014, they added an option to search for non-touching faces in the global contact. I've had limited success with it, to be honest. You know, you're welcome to try it out, but I've had better success by just assuming that I'm going to have to deal with any non-touching faces manually. The other situation where we may need to manually address contact interactions is between meshes of different types, between beams and solids, solids and shells, and beams and shells. And in those situations, we define the contact relationships manually. So let's have a look at this. Let's start off with a couple of neat tools. Well, we'll start off with one neat tool and we'll finish up with another one. I'm betting everyone in here has used interference detection before in SOLIDWORKS. It's a great tool for figuring out if any parts run through each other. What you may not be aware of is an option here to treat coincidence as interference, and this will highlight touching faces between parts. So if you're not sure if you've got like a tolerance gap between two parts or a weld gap or anything like that, this is a great way to instantly visualize where those contact interactions lie. Okay. But if we're looking to define contact, I've got some contact that I need to define. So in this particular case, in the right-click connections go contact set, I need to define an interaction between the tank wall, which is defined as a shell, and the inner surface of these plates. Just click there. Should always be looking at my selection list to make sure I'm getting the one I want. There we go. So that's just going to tie that shell and these solids together. I'm going to hit this push button here, and I'm not sure if you're aware of this. It took me about a year to figure out what it did. It keeps this information on the screen so I can go pick something else. I also have an interaction here between beams and solids. Anytime you connect with beams, you've got to select on the little object here to connect beam entities to something else. Beams have to go in the first box. And if you pick the surfaces of the beam, it won't work. Because as soon as you create a beam mesh, it effectively deletes the real surfaces and replaces it with an analysis entity. So I've tied those things together. You know, I may have a situation here where I want to bolt these parts together. And if you're bolting parts together, one of the key things is that you need a no penetration relationship between them, right? If you assume those two parts are glued or fused together, there's no point in having bolts, so we'll do that. So something that's new here in SOLIDWORKS 2014 that's really great help is something called a contact visualization plot. We'll do a couple of things. I'm just going to mesh the model very quickly here, show you a couple of things. So yeah, this contact visualization plot will actually show you on the screen, first of all, what relationships you've modeled, both from the global contact and manual things we've applied. Right, by coloring the interface with a color appropriate to the shape of the interaction. All right, so that's good. It can show you what you've missed. And if I'm looking really carefully here, I'll see that I'm missing an interaction between the top of the saddle and the thing below it. I've actually got a gap there, so that's something I need to resolve. You can turn on this option to include solver-based contacts. It will run a couple of seconds of the analysis and then actually show you which elements and which nodes are mapped to each other. Right, sometimes as you run things like this, if you've got a fairly coarse mesh, it can actually map, that bonded interaction to, in this case, a fairly uneven patch on the other part. So we may want to look to refine that mesh around that interaction to improve what that mapping looks like. But until now, we've never been able to visualize exactly what that mesh mapping looks like. So that's a pretty neat little tool. So contact is a big part of that environment. The other big part is connectors. And connectors are really virtual analysis constructs that tie objects together, right? And so we've got options for bolts and pins and springs and rigid connectors between two nodes and links and things like that. But one of the most common, the one we're talking about, is a bolted connection. Okay, and a bolted connection is actually developing a fairly complex analysis construct with minimal information from you. Okay. What the software does when we create a bolted connection is it develops a beam element and rigidly connects it to the interfaces for the holes. So if you've defined it as a nut, right, it interfaces to the back side of the hole. If it's threaded in, right, it'll tie it to the inside of the hole. But it creates this beam element and spider connectors to tie it to the right information. And then it can put that beam element into tension to simulate the preload on that joint. And that's often an important part of a bolted connection. Doing this manually is incredibly tedious. Right? If you were to go back 10 years and use a different analysis tool, it is incredibly painful to build these elements. And the good thing about SOLIDWORKS is it interrogates your model and basically says, hey, I know the size of this hole, right? I'm going to construct this geometry automatically. I'm going to tie it to the faces you told me to tie it to and just go forward with it. You don't need to understand the underlying analysis technique there. It'll go off and report the axial load, the bending moment, and the shear force exerted on that bolt. And SOLIDWORKS 2014 is taking it a step further. If you have used components from the toolbox, all right, nuts, bolts, and screws from the toolbox, as soon as you open a new analysis, it'll ask you if you want to convert those toolbox components to bolted connections. And it'll actually interrogate the size and the head diameter from the toolbox. It'll have it as a lookup table of recommended torque values for that size of screw or bolt, and it will apply those automatically, and you can edit them if you need to be. So very, very quick process. In terms of fixtures and next phase is how this object is held. And when we create fixtures, all we are doing is removing the ability of certain faces or edges or vertices to move in a certain direction. We're just removing degrees of freedom as we talk about it. Right. So solid mesh has 3 translational degrees of freedom. So if we fix something, we're preventing it from moving in X, Y, and Z. Shell mesh has rotational degrees of freedom that we also need to consider. And all our options in our fixture environment here, fixtures, they're just ways of removing different degrees of freedom. Fixed, everything is removed. Roll a slider, only 1 degree of freedom is removed. It can't move off plane. Fixed hinge, right? All degrees of freedom are removed except the ability to rotate. But I want to draw your attention to what I call the granddaddy of all fixtures in SOLIDWORKS. It's a tool that can be used to develop any of the other fixture options, and it's called Use Reference Geometry. Here's how it works. Whatever you put in this pink box down the bottom here defines the reference or the coordinate system that you're going to fix something with. If I pick the front plane, it sets up an XYZ coordinate system relative to that front plane. And then I can go in and remove individual degrees of freedom relative to that. I can prevent it from moving normal to that reference, in plane with that reference, and so on. And your fixture arrow should update with the information as you develop it. Just by turning these on and setting it to 0, you're preventing it from moving in that direction. If we put something different in this box, if we were to pick something cylindrical, it sets up a cylindrical coordinate system. And so now my degrees of freedom are radial expansion, circumferential twisting, and axial motion. So I can control those. And there's another set of tools for if you have a spherical reference specified here. Every other selection that's possible through here is just a subset of what you can create with the use reference geometry. Cylindrical automatically sets up a cylindrical coordinate system. So in fixtures, we're just removing degrees of freedom, and we're doing it to represent a connection with the next thing that we haven't modeled, whether it's the wall or the floor or the frame that it sits on or whatever it might be. You know, that fixture is representing that other body that supports or restrains the model. So you can get a lot of information from the preview that you see. You know, arrows represent translational directions removed. Little wheels at the back of the arrows represent rotational degrees of freedom removed. And if you're not seeing those fixtures, those previews, you want to go to View Simulation Symbols, and that will toggle all simulation symbols like fixtures and that sort of stuff. It'll toggle them on and off. The View Simulation Symbols, the place to go. They can get a little intrusive if you've got a lot going on. You can also hide them item by item by right-clicking on the item and selecting Hide. But the last main piece of user input that we've got here is loads. Right. And I find this is normally the easiest part of the process. This is what your standard or your test plan says. I need to see how this responds to 100 pounds of loading, or it's being subjected to 50 psi of pressure. Right. And so many of these inputs are pretty self-explanatory. Right. It can apply force, torque, pressure, gravity. Gravity is the self-weight of the object. Things that are rotating, we've got centrifugal. We can import thermal effects from stress analysis, from a thermal analysis. We can apply a certain temperature change, see how things expand and contract. But something that confuses a bunch of people are these other options, remote loads and distributed masses. But first of all, another thing we don't get a question about often, but it does occasionally come up, is, what's the difference between a force and a pressure? Does it matter which one I specify? And the short answer is no, right? A force applied to a face becomes evenly distributed across that face, unless you set it to something non-uniform. And if you apply a pressure of equivalent value, you'll get exactly the same result. The main decider of which one you use is what unit do you have your input information in. The force unit, just apply a force. Pressure, vice versa. And rather than doing the math to convert one to the other. So let's prove that out to you. If you need it proving that. Here's an example. We have a 1 inch by 1 inch boss here, just to make the math nice and easy. First example, we have 100 pounds of force applied to it. There is one gotcha I'll get you to watch out for. If you pick multiple faces, this option, the per item or total, lights up. If you ignore that and you end up picking the wrong thing, you can end up with in this case, 3 times the load you're expecting applied to this model. Whereas total is going to distribute it based on surface area. Okay, so this one's going to get most of it. These smaller faces will get a smaller proportion of it. But in this case, I really just want to apply it to the top. Apply 100 pounds of force to the top. I can run the analysis, and I can get a result where the displacement is, in highly scientific terms, lots of zeros and then 17. Okay, so remember that number. Option 2, we can apply a same load with 100 psi pressure. And with the pressure, it doesn't matter how many faces we pick, it's per unit area. So we'll always end up with the same pressure. There's no total or whatever option. 100 psi over 1 square inch, that's going to come out to 100 pounds of load, and surprise, surprise, when you do that, we get exactly the same answer. Good, so force and pressure are the same. What's a remote mass or a remote load? A remote load is a load that is considered to be acting at a certain point in 3D space, right, defined by some coordinates here, but operating up here, that acts in a certain direction, and it is connected to the rest of the model via a series of rigid bars. Okay, so it's almost like saying, hey, there's a bunch of intermediate geometry here that I'm going to eliminate and represent the effect of that action with a remote load. And if I apply a 100-pound remote load on that top surface, still 17, right? Same value. What's a distributed? The other option we might have is a distributed mass. A distributed mass is like painting that top surface with magical heavy paint, right? We've added 100 pounds of load to that top surface. It doesn't act in any way until I turn on some sort of gravity, right? If it's floating in space and zero gravity, it doesn't have any effect. But as soon as I turn on gravity and give it a direction, it acts heavy, and hey, that 100 pounds gives exactly the same result as well. So if the distributed mass and the remote mass give the same result, what's the difference? Well, the difference might become apparent if we flip things, right? If I set this thing up sideways. Now when I apply a 100-pound load downwards, I'm not only pushing on the model, I'm also, with the remote load, including a moment arm. So now when I run this analysis, I get something a little bit different because I'm twisting that object. Right? There's a moment couple that's operating there. And that's the big thing that remote load gives you. Not only the loading, but the couple. If I did distributed mass right on that face, I don't see that same, well, that same coupling effect. So I get a very different answer. There's some other idiosyncrasies to that tool. There's some pretty good help menu descriptions of remote and distributed mass that I'd recommend checking out. But the key difference between a remote and distributed mass is whether it adds some stiffness to the model and it includes that moment couple. Okay, we're getting pretty well through the process. Once you've done your model definitions, shells, beams, and whatever, shells, beams, and solids, you've done your contact, you've applied some connectors if you need them, you've considered your forces and your restraints, you're getting to the point where you're ready to mesh the analysis. And just to highlight, the full setup here, one of the main unique things I have in this model is this tank is filled with water. And so to represent that water, there'll be a pressure gradient as I move down the depth. So I've defined something called a non-uniform distribution, where I've set a coordinate system at the top of the model. And that pressure will increase with depth. When I activate the tool, if you look at the red arrows, particularly over here, they're a lot bigger as they get towards the bottom. But the main situation you use that, it's liquid that's in a tank, so pressure will increase as you move down. That's the main loading I've got on this particular model. Got some sort of end load that's being applied. It's well. So next phase is to mesh the model. And one of the main choices, you have two choices when it comes to mesh. First of all, which algorithm do I want to use? We have two, standard and curvature-based. And then you have choices over the size of the mesh. And whether you want to set that globally, the same approximate instruction applied everywhere, or whether you want to refine it in areas of the model. I'd certainly recommend using a tool called Mesh Control to refine areas of the model that are of particular interest. We're going to talk about this in excruciating detail next time up as we talk about mesh convergence, one of the key things. But in terms of the two algorithms, I'm going to draw your attention to a model here that I've got that's intentionally annoying to mesh. Right? It's been created solely for the purpose of being a pain to mesh. So the reason it's a pain to mesh is we have small features that are closely grouped together. Right? It's going to be hard to map and mesh element through there. I've got a whole lot of detail. I've got thin sliver faces. And I can do this two ways. I can activate something called the curvature-based mesher. Let's mesh that live. Okay, it's going to process in about 10 seconds, and it's going to require, this is completely default settings. Right? No manual adjustment required. Curvature-based mesher is scanning the local curvature of the model. Right? And it's applying a mesh algorithm based on that local curvature. So very big cells in this open curvature area, smaller cells through here. The standard mesher, which is kind of the legacy mesher that we've had for a long time, that will fail if you run it with default characteristics. It basically interrogates all the faces in the model and tries to seed a mesh on each of those faces and then tries to push it through the thickness. It is possible to mesh this model with the curvature-based mesher. However, I had to manually control 133 faces to get that done. It took about 33 seconds to mesh versus the curvature-based mesher. So in terms of just getting a mesh, the curvature-based mesher will generally be more efficient, and the main reason is it takes advantage of multi-core processing. Right? And it is what I use as my default now. It may create a few more cells, but I'd rather have a few more cells than spend 20 minutes of my life adding mesh control to 130 faces in this model. So that's a general recommendation for now, is use the curvature-based mesher because of that multi-core capability. And in a similar vein, if we look at actually hitting run on the analysis, you have two choices available to you. You can either use something called the Direct Sparse solver, which is a direct solver that directly solves the system of equations. And that is very good at using multiple cores. Right? If you've got lots of processors on your system, that's the way to go. However, it uses significantly more memory. The FFEPlus solver is an iterative approach, a guess and check approach. It doesn't use multiple cores as well, okay, because it has to guess and check in order before it can do the next step. But it is very memory efficient. What that means for us is that on small problems, Direct Sparse solver will be a lot more efficient, but as those problems get larger and the RAM requirements really ramp up, the FFEPlus can become more efficient. And at least that was our story up until now. And then in SOLIDWORKS 2014, SOLIDWORKS introduced something called the Large Problem Direct Solver, which has many of the advantages of the regular Direct Sparse solver with less memory usage. So it's new in 2014. We haven't had a lot of seat time with it. But the one takeaway that you should remember is that regardless of which of these you use, you should get the same answer, or very close to the same answer. The real decision point is how long it takes. There's a couple of situations where one of these tools is not appropriate, and the software will warn you and automatically switch the solver. For example, if you try and run a frequency analysis with an applied load, FFEPlus won't work, and it will tell you and switch the solver for you. But one thing to point out is that the solver choice is defined in the properties of the study here, and there's an option for automatic. Automatic will automatically select the best choice based on based on the size of the model. It'll make a selection and toggle between FFEPlus or Direct Sparse. Okay, we're getting pretty close to the end. Let's assume that we've hit run on this, and we've got some results to look at. Okay. When we look at results, we have a wide range of result quantities that are available to us. We have a variety of options for viewing those, but in terms of just listing out all the things that we can look at, right? We can look at the individual stresses in a model in any of the X, Y, Z directions. So I can, if I edit the definition of this plot, I can look at stress in the X direction. If I want to change the X direction from the orthogonal, the model X, Y, Z, I can just pick a reference here. Right? If I had some angled plate that I wanted to measure stress relative to, there's a reference there. So I can look at stress in X, Y, Z and shear stress about those three directions. No problem. The problem, well, one of the challenges is kind of the net stress and overall assessment of stress in the model can only be made by some combination of all 6 of those states. So one way of combining those states is to consider the principal stresses. Right, so these are, if you orient the unit stress element in a direction where there are no shear stresses, you'll get 3 principal stresses, P1, P2, and P3, and we can interrogate those. And we can look at the directionality of those if we wish to by showing as a vector plot. Right, so we'll show the principal stress direction for every single element in the model, and you can control size, shape, and density of those vectors. When we look at displacement, we can look at, the distortion of the model in X, Y, and Z, or we can look at an overall resultant direction. And when we interrogate these plots, we get a lot of options available to us. We can choose to section the plot to take a look through the thickness. Once we have some sort of plot, one thing that always gets me is that it took me forever to realize. If you have sectioned something and committed to it, it's not immediately apparent how to get rid of that section. I don't know if anyone's ever seen that. The trick is go to section clipping and then click the unlabeled button at bottom left to turn the clipping off. For a couple of years, I was recreating a plot if I did that, so I couldn't find the switch. You have probe capabilities that allow you to basically pick any point in the model and get a real value read off of whatever the current stress state is. That's a good thing to do. And you have complete control over how things look in this view. Now, it used to be that you had 3 places you could define how things look: edit, definition, chart option, and settings. And you still see those 3. But if you enter any one of them, the other 2 areas where you can modify things are in tabs now. They're all coherent. So if I want to show the mesh, I can do that. If I want to change the color chart to something more interesting, like rainbow can be interesting. And if I want to change the unit that I'm displaying things in, I can do all of that from one interface. Instead, previously it would have been three 3 different menus I'd have to go into to adjust that. But one of the key things that we want to do when we finish up a stress analysis is make some assessment of performance, right, or failure, of determining how close we are to failure. And we're typically going to use some sort of failure theory. General concept of a failure theory that basically says, when I combine all the stress information that I have, present me with a single number that I can go compare to a failure limit and make a design decision from that. That might be as simple as looking at the first principal stress and comparing it to the tensile strength of the model or the compressive strength of the model. Really common one for ductile metals and also a variety of other scenarios is a von Mises approximation. And this just combines the 6 different states of stress, X, Y, Z, shear stress about those 3 axes. It combines them into a single value. It's expressed on the screen there in terms of principal stresses. You can also write it out as part of, as a combination of X, Y, Z stresses. But essentially that von Mises theory is just giving you a single value that you can compare to the yield strength of the material. And so how do we tell the software to use that? Well, we can just ask it to show us von Mises stress, remember this number, and go compare it to whatever my yield strength is. You can also define a factor of safety plot. Okay, and a factor of safety plot lets you define the failure theory. Go for von Mises stress here. Right. And so it's going to show me, it's going to compare the von Mises stress to the yield strength of the material and present me with a ratio. And my minimum factor of safety here is 0.98. Now, von Mises is just one failure theory. Another common one is what we call Tresca, or maximum shear stress theory. It's basically saying P1 minus P3, principal stress 1 minus principal stress 3, that's my stress limit. Now, Tresca is almost always more conservative. That means it'll predict failure earlier than von Mises. The only situation it won't is in a situation of pure shear stress where it predicts failure at the same point as von Mises. But we can switch to that. Well, we can either look at a stress plot, calls it a stress intensity, but we can modify it here to failure theory, and you'll see the minimum factor of safety using this different failure theory is now 0.86. So it's more likely to fail. This is more conservative. Now, you'll have some sort of, depending on how conservative you want to be, or if your standard instructs, you know, what theory to use, you can do that. But von Mises is the most commonly used, especially for ductile metals. If things are brittle, they don't fail the same way. And so we actually have another failure theory built in for brittle materials. It's a more Coulomb stress theory, but all that's doing as well is looking at the stress components in the result and combining them in a different way. All these failure theories are just combining the underlying stress information in a different way. So, you know, the most common way to predict failure is to take one of these failure theories, compare it to the failure limit that you have, whether that's a minimum factor of safety or a maximum stress level, and make an assessment from there if it's safe or not. And so that brings us pretty much to the end. I apologize, I'm a little 7 minutes over here. That's most of what I wanted to cover today. Well, we're going to focus, so we've basically been through a stress analysis process and talked about some of the underlying inputs and as best as we're able to do in an hour. So coming up on Thursday, Damon will take us through some common troubleshooting issues, things that we see over tech support where people have problems. We see them over and over again, so we thought we'd talk about them. And some strategies for making sure your stress result is accurate before you go show it to someone. But before we finish here, I want to introduce something to you. It's not yet available, but it will be very, very soon, and it's part of our Hawkware initiative. Hawkware is a series of applications that do different tasks in SOLIDWORKS. And we're always looking for things that cause people pain and see if we can find ways to adjust them. It's a plug-in to the SOLIDWORKS environment. This one's a free download, so it costs you nothing. I've got a beta version attached, but this is called the Simulation File Manager. Basically what it does, one of the challenges with simulation is it creates a bunch of files on your hard drive. Okay. It creates a lot of those as it's doing its working, and not all of them are required to actually see the result. Let's take a look on my hard drive here. Just bear with me, I'll just navigate. Okay, this is my folder that this tank is in. Here's my results folder. Here's all the stuff I have in there. I have, for example, the one that's solved has 31 files with about 260 megabytes of space. And when I look at the one that's called solved, here I've got all these different files, alt, RLC, SL1, SL2. The only one I actually need to show a result is this one right here. So what we can do, just close that result. What we can do is we can check that box and say archive, and it's going to go into that folder and clean up all the stuff that isn't required to show a result and pack the result into a zip file. I'm going to delete out all the junk and compress the one so I can pack it up. You know, this project is done, I want to move on and conserve this space. If I want it back, it's just a check mark and hit apply. And it will unpack the result, but all the extraneous stuff is gone. So it's something we're just dialing in the last pieces of. You'll see that up on our on hawkwareapps.com pretty soon. But if you go up there now, there's a bunch of other tools for SOLIDWORKS. There's both paid and free apps, and what we just saw was an example of a free app. So that's pretty much it for today. Thanks for everyone for joining us. I will be sticking around for a few minutes here if there are any additional questions. Feel free to fire into the chat interface if you have anything you'd like to ask. Always like to put up our tech support numbers there. If you have any questions on anything you're doing in SOLIDWORKS, that's a good place to start with us. And otherwise, thanks very much for joining us, and we hope to see you on Thursday for part 2 of our night school session.